Welcome everybody, and myself, Dr. Liang already introduced, and myself, as said, from China to United States to China, over 40 years, full of joy. All right, as a professor, it's really fun profession. I graduated from Beijing University, and then we went to US for 30 years. Eventually, in response to our government and the colleagues' call, come back to Tsinghua University 2009. Very happy things, I could say. In May, Tsinghua University and my big group, we graduated 8 PhD students. That's one I'm very proud of. All right, come to our topic. So I'm going to talk about photothermal conversion material, which somehow is related to carbon capturing, right? As we know, sun is the one give us most of the energy, except the radiation energy from the formation for Earth. The rest energy almost all from sun. They give up warmth, energy, and the carbon capturing. Everybody knows the photosynthesis, or this photochemical conversion. So the chemical energies, right? We get the electricity. Now the photothermal conversion, we got the internal energy. So that's our topic. How to utilize the sun or green photo energy to do whatever we would like to do. So photothermal energy conversion is basically freshman textbook stuff. And when a material exposed to sunlight or any light from the electron from ground state to the excited state, they have several ways. Either they come back emitting fluorescence, or doing the intersystem crossing, get the phosphorescence, T1 state. Most of those light energy, it's very small amount. All photoelectronic energy, very small amount. Most energy from sun, from light, that become the heat dissipation. All right, become heat. Okay, now what do we like to use those heat? Myself, my research covers all kinds of stuff. Start with organic polymer synthesis. When I was undergraduate student till now, and then 1990s we get into inorganic material, mesoporous silica gel, silicon material, more of course. We did a lot of inorganic stuff, and since 1997 we get into biomaterial from protein to DNA, to cell culturing, to tissue engineering. So we like to do all kinds of fun stuff. All right, today what we're going to do is talk about three things: the photothermal conversion materials. The material in terms of three aspects. One is solar distillation or solar desalination, whatever you call, for fresh water, from seawater or polluted water. The second thing I like to do is use like a carbon materials, carbon nanotubes or graphenes as the solar conversion ingredients to incorporate into a new material called richmers, which is liquid crystal elastomers and shape memory materials. The third is photothermal and the photodynamic material for tumor therapy. So in terms of scale, the first application is big foam, like our sponge. used in kitchen. Okay, secondly is bulk material, our ingredients. In the beginning, we use carbon nanotube. The third one, this is photothermal conversion nanoparticle, 15 nanometers or so. So I'm going to basically talk first two. If I have time, I will talk a little bit more about chemotherapy. The first one is solar distillation for fresh water and seawater. So here we used the things I did like 40 years ago, the conducting polymer, which is really important material nowadays. Now, the background is the crisis of fresh water, particularly in China. Okay, China has 20% of the population in the world, but we only have 6 or less % of water resource. Therefore, to get a drinkable fresh water is a major challenge. Another thing is, of course, with drought, right? Africa, not too long ago in China too, the drought with lack of water. The second thing is we have high polluted water, industrial pollution, all the oil tanks spewing oil. Okay, now it's very important to solve that problem. How to solve that problem? So this will I will use this 2000 Nobel Prize in Chemistry, Professor Alan McDiarmid is my honorary mentor. This is conducting plastic. Plastic is not conducting electricity. Everyone know nylon is here, diamond, glass, it's 10 to minus 10 conductivity. However, some organic compounds like polyaniline or polyacetylene, they are not conductor at all. However, upon doping, they can jump the conductivity for like 10 order of magnitude, become conductor. Therefore, once they become conductor, therefore, they get a Nobel Prize, and then there are many applications. Right? Since then, we're not using the conductivity to fabricate all kind of useful materials. Instead, we can use conducting polymer properties to fabricate the chips or the display device or wearable. Now it's really hard, soft wearable clothing. Now, those are based on the photoelectronic effect or reverse electricity-driven luminescence. Now, another very important area is organic solar cells. There are many advancement or breakthroughs recently, popular, at least 20 some science nature papers. However, regardless in the paper, the report up to like 20 some %, everybody knows, even pure silicon, their photoelectric efficiency is about 20 something. All right. Organics normally for practical applications, nobody can go over 14%. All right. So that means 100 photons shine on the material, only 14 photons convert to electrons. Where the rest of solar energy went, okay, 86 photons. Where did it go? Okay, they went to heat dissipation. Now for the solar distillation, we do not want the electricity at all. We try to avoid the electricity. All we want is heat only. That's we come into this project. That this contributors led by Professor Jian, okay, Professor Chao Mei, Professor Yang, they are all graduate, Dr. Li. Okay, so how to get fresh water from seawater? This is ancient stuff. All right, everybody knows if we do the distillation, seawater for here, put some chips, and then heat it up, and then condense, you get the fresh water. However, this process is very expensive. And the second thing, most rural use this osmosis method. Okay, seawater and the fresh water, and then you put a high pressure on the seawater side and force the fresh water past the membrane, collect the fresh water. Again, it's also very expensive stuff. The third one is everybody watching the movies, like survival in the wild, right? So all you have to do is the sand beach, you dig a hole, put a plastic on, and collect some fresh water overnight. That's all very low efficiency. Now, that comes out. If we put a material, artificial, we create a material on the top of seawater, they can suck in all the sunlight, absorb all the sunlight, and then evaporate, and we correctly evaporate the water, and then we get the fresh water. That's the strategy. In this case, of course, this piece of material is extremely important. All right, so people realize how important this topic is. There are at least hundreds of papers published. Use this material, one type of material is metal nanoparticles, particularly like gold nanoparticle assembly. So this gold assembly can absorb almost all the sunlight. Okay, and then release heat and to get water. The second one, lately very popular, is the carbon materials. You can have carbon nanotubes, the graphene sheets, everything. Also a lot of paper. But these two materials, as you can see, have some really serious problem. One, if you use gold, it's too expensive. We like to do a couple of square kilometers of ocean surface. We do not have that much gold. Okay, if you use carbon nanotubes, it's really good, but the nanotube is very nano. Okay, and then if the seawater is dirty, they're blocked. Okay, another thing is they don't have good mechanical properties. For example, we put a graphene into seawater after few hours or few days, the graphene become must, right? Okay, decomposed into small particles, useless. So our group go and achieve use very cheap materials, aniline, polyaniline oligomers, which is invented in my lab. We use the foam as a sort as this interfacial foam. Therefore, you have a very simple, very cheap preparation, very cheap, low cost. We can control the pore size. Okay, we can do large scale production. Now, what's this aniline oligomers? This is the one of my early papers. When I become assistant professor, we invented this process and prepare this aniline oligomer. You can see that's a conjugated system. Okay, 3 nitrogen, 4 nitrogen, 3 benzene. That they are conjugated. Okay, therefore they can become a conducting polymer, can become a so-called electroactive materials. Now we use this material. This is very easy to prepare. We can prepare, one freshman can prepare 10 grams or more a day. All right. But this material, we have an amino group, end group, see, NH2, NH2. Once we have that group, NH2 will do so many organic reactions. One of urea reagent, right? We use all the time. It's a urea has an NH2 group mixed with formaldehyde. Okay, they form a polyurea material. So we use the same strategy. Use this electroactive oligomer. Use formaldehyde to the cross-linking. Cross-linking. Therefore, we can get an extensive network of electroactive aniline oligomers. So we prepare foam, we use the simplest method, we use the salt method. When you do the preparation, put a lot of salt in, and then you wash it with salt, we get foam. So this foam, we can control the morphology, we can control the pore size, okay? For example, we can control the pore size very small or very large. In case of dirty water, we need a large pores. All right, this material is typical cross-linking material, have very strong mechanical properties, you can see, and have all excellent anti-solvent or anti-base acid, anti-solvent, okay, have good mechanical properties. You can soak that in seawater for months without decomposition. Now, this is a key point. We put this material, the foam, at this is seawater, okay, at the interface, and then we shine lights on. At the interface, the seawater temperature, just 10 seconds, increase temperature to 60 degrees. Okay, that's red line. At the interface is 60 degrees, then the water vapor, of course, getting out. We can collect the water vapor. That's our fresh water. In the meantime, of course, the hot water getting out, and then the bottom, the water still cold, 20 degrees, see? And then bottom water continuous going up, get to the interface, and then get fresh water out. Just this process, we can produce large amount of seawater. This, of course, is just one sun photo solar light. Okay, 10 seconds, we get 60 degree water come out. Now, how to do the experiment? Very simple. We have analytical balance, and then this is seawater, and we'll put those aniline oligomer film on, and then we put a solar simulator on and shine the light, and the water evaporates, and then we hook the computer. We can do all kinds of kinetics, thermodynamics analysis. Now, the result. Oh, wait. This all important slide. Okay, put the material on. This aniline foam has very good light absorbance. You see, from 200 nanometers to 2,200 nanometers, almost a complete spectrum of sunlight. All right, we shine light on, we found the absorption rate is about 90, lowest 0.80%. That we can capture all the photons, convert to heat. The 0.5 sun shine stress, you can see temperature increase, to like 60 degrees. One sunlight strength, 10 seconds, 67 degrees. If two suns solar the photo strength, we can get to like 100 degrees centigrade, which of course 100 degrees is the water boiling point, right? Therefore, we can achieve this distillation. The distillation water come out very pure. Okay, this is seawater stimulant, 3.5% sodium chloride. After distillation, we can get very, very pure fresh water. This is a log scale. All right. After distillation, the content of sodium chloride is less than ppm level. Potassium, calcium, magnesium chlorides in the seawater, after such kind of distillation, they all at the ppm level. All right. Not only seawater and other mixtures, it's the same way. Polluted water or sodium hydroxide or sulfuric acid or organic stuff, rhodamine or milk or mixed solution or all kinds of things. We can get almost pure fresh water out. All right, so we're trying to do the relatively large scale. My student, Dr. Lee and Mr. Wu, the PhD student, they constructed a lot of glassy houses. Okay, put the seawater in, with the foam in, you can get your fresh water out. All right, so we build a big, like housing village. So to produce these things, all right. Not only that, okay, we can. This is a Professor Dai at Dongnan University. He published a beautiful paper. Well, to get the fresh water, what we can do is only during the day, right? If rain, we don't have much sunlight. Night, we don't have much sunlight at all. So Professor Dai used a phase transition material during the day, absorb enough sun energy. During the night, this phase transition material can release those, maintain like a 24 hours working of this solar distillation job. Recently, just a few days ago, this is very interesting. This is Professor He Si-Xin, Harbin Institute of Technology. A beautiful work. So the combined material, this is Young's phase material. We have graphene, we have sponge, the melamine sponge. And then have three functions. Number one, they can do all day long solar desalination and take advantage of when the water evaporates, the salt concentration becomes large. Therefore, we have an electrical engine, generate electricity. All right, and then another thing is just a few. Not too long ago, the material is the polymer. People always think about microplastic or polymer plastic pollution on the ocean. So Professor Chen invented a material is used Richmond. This material is with the epoxy material, and then you can do your solar distillation, and then this material can be recycled. Okay, you can collect them back, recycle them, release the pollution. From that, we'll get into the second topic. Second topic is liquid crystal elastomer, the shape memory material. With shape memory material, everybody knows, right? Started with a nickel titanium 100 years ago, and then you make a shape, all right? They'll after heating or photo exposure, they will go back to the original shape. All right, this material is extremely important. Now, we get into those projects mainly by Prof. GM. All right, this one was quickly go through this. Is a movie, Schwarzenegger, right? Remember that movie? Movie has a very special material called a P1000 material. Those material have what? Flexible motion. They can change the shape. Okay. Another one, healing wounds. You can shoot them or destroy them. They can heal wounds. Then they can reassemble, detach upon you, cut off the hand. They can put it back and recover from distortion, regardless of you distort them or wide temperature range. At the liquid nitrogen temperature, they still work, this material. Okay, so this material is called a liquid crystal elastomers. This material is based on liquid crystal principle. Normal liquid crystal, this blue bar. It's a liquid crystal unit. Okay, when they are in random shape, you can see they are isotropic material, photo or physical properties isotropic. However, once you orient them, okay, they line up, they become anisotropic material. Therefore, we have a photo display, all kinds of television stuff. However, we notice that the change in the physical dimension. Once they conserve the volume, this one, of course, the z-axis is smaller, but once you orient it, the z-axis become longer. That's our actuator. Okay, change it from this two states. You can lift the weight. This change can be by heat, by thermal, or by light. That's the essence of science, very simple. And the synthesis is very simple as well. This is liquid crystal unit, and then you just do epoxy ring opening formalization, you get the material, very simple. And this material is at a high temperature to shrink, right? And low temperature to expand. And we can see those crystal oriented very well. And we can use light to achieve the same thing, the shape change. So this is a classical original work. You can see we can program those shape change from which dimension to another dimension. Therefore, we get this piece of liquid crystal elastomer. The black thing is what? So we dope them with the carbon nanotube, because carbon nanotubes have very excellent flow to thermal conversion effect. Now, once we heat it up, cool down, okay, you can see the chair, the leg going up, going down, the chair back going up. You can make all kinds of things. That's stable memory, and you can make a weightlifting man, again, lifting heavy weight by changing temperature or change the shine light on it. All right, you can make a little worm. They can move. You can program every leg, 3 legs in, you shine light on one leg they will go forward or backward. Okay. And then you can program any shape you want, like this little piece. If this arm we program up on heating or cooling or shine the light, they go up or go down. You can design any shape you like. And then once you reverse the temperature, they go back to the same shape, the reverse, and then you can reprogram to other shape as well. All right, so once this material we get it, you can shred them, all right? Yeah. And then upon changing the temperature, they'll go back, see? All right, you cool again or shine light again, it goes to another original shape. All right, so that's they can get a recovery from distortion, and then can also do the photo welding. Two different elastomer rubber material put it together, shine light on, they weld together. Okay, and maintain excellent mechanical property, and the two pieces of elastomer, they have different properties. We can program them to do the shape memory stuff. All right, so this is original piece of material, and then we weld another material to it, and then you create all kinds of shape. And the temperature or photo, you can make all kinds of shape, all this like graph stuff. Okay, and then we can make all kinds of fun stuff. Now, they can do the hearing, all right? If you use a sharp knife, cut a line on the material, and then shine light 5 seconds. This wound disappear. Okay, the large wounds, that's used. Large knife, you cut them, and shine light 10 seconds, they're gone. Or use a pin, like bullet hole, right? That's a push pin. We make a hole and shine light 10 seconds, it's gone. Okay, so at the low temperature, we can do the same thing, to minus of 130 degrees centigrade, and then we put it at a little insect there, and then we use photo driven, they can still move, they can still do photo welding, you can do the wound healing. Therefore, this material is almost like the science fiction can do everything like a Terminator can do. The new Terminator today, I will not talk about. Terminator 2023, we are exploring the combination of liquid crystals, Richmond, and other polymer system with the liquid, liquid metals. Okay, right. And next time, if I have a chance, we can discuss that. And after original work, and then we expand our work tremendously, okay? We can make all sophisticated shapes. I can make sensors or actuators, or you can make that's like a jellyfish or propeller, all kinds of things. And then recently, that's very interesting, this Professor G and the student made, it's a two different piece of material, the property is totally different, okay? When you squeeze them together at the interface, they will have dynamic covalent bond exchange reaction, okay? Then they form very, very tight interface. Two material, through the tiny interface, they become one material. This applicable, almost universal. We did ester bond, this is urea bond, okay, boron, and other stuff. Okay. We can put them together. Recently, this is we can make it again. That's our student made all kinds of funny shape, flower, everything. Well, this I have to talk about. This is Dr. Liang, just graduated, PhD. So everybody stretches rubber bands. These are rubber bands. You stretch them, you hold them, right? This rubber band will not do nothing. When you release the stress, they will come back, resume original state. However, for Dr. Liang discovered this rubber band, once you stretch for long enough time, bang, they have a muscle come out. See the bubble buckling up. All right. So the material, you see, normal rubber band, stretch them, and then after a while, you see, some section, they were bulging out. And if you change the condition, they will go back. That's the reversal process. So that's figure out what happens, the mechanism, the applications, the imagination limit. So there's Dr. Liang figure out one remote controlled self-terminating circuitry. If I put a rubber band between two electrodes, right? And then the rubber band is short enough, the conductivity of the electrode is still there. So the circuit is open, but after a while, the buckling happens. Also, automatically disengage this circuitry, right? The buckling happens, the circuitry is closed. All right, that's one simple application. And then we're thinking about the insert them into the blood vessel or the surgery stents. Maybe we'll get some fun results. All right, to summarize, this is just a simple concept. The liquid crystal, when they randomize, the dimension change. Once they oriented, the change, the bend change the shape. So we can find out many biomedical or whatever application. Last, I just spent 1 minute talk about this, okay? The photothermal and the photodynamic material for tumor therapy, that's fun stuff. Of course, we have a big team doing this. Photothermal precision diagonal therapy. Here what we do is, I'm interested in tumor and cancer, of course. This is 2015 data. The cancer crisis in China and in the world, right? The tumor, how to kill the tumor, everybody knows. Surgery to cut them out. The chemotherapy very painful. Radiotherapy very painful. Now, recently, immunotherapy, this based on genetic method or other method. Okay, but they all have very poor performance. So now the one thing is ancient, as ancient as 2,000 years ago. If you cannot cure a disease, you cannot cut them out. What do? You burn them, right? Burn them. That's called nanophotothermal therapy. Some of them have been applied in clinical situation. So this principle is very simple. This is photothermal nanomaterials, biomaterials, and then you shine them with near IR, okay? And then to convert this photo energy into heat. As long as the heat temperature, thermal temperature larger than 47 degrees or 40-some degree, you know, all the biomaterial, the tumor or virus, they all die, right? So that's the principle. The design is here, early design, we put a gold particle, which is very good thermal conversion material, and then we put the antibodies and put the polymer arms. So on that, we get a nanoparticle, and then get a nanoparticle. We can put all kinds of functional group there. For example, like dyes, we can show where the nanoparticle goes, and then we make those nanoparticle and did a for nucleamize the skin cancer. Use our method shine the light. You see the tumor disappeared. Okay, another one is use organic tumor, organic material with conducting polymer again. That's polypyrrole, another conducting polymer. We can combine, start with a protein, we can add the dye stuff and show us where the particle goes, and then we can put a biocompatible RGD to the end. And then we can put a poly. This is a this is a Paxil anti-cancer material. We get composite nanoparticle. This nanoparticle, the size is about 15 nanometers. So we can control them, and then the diameter distribution is very good. And then those particles inject to the body. You can see them. Where did they go? They go to cancer cells. All right, and then this is a live photo of the mice. You can see the cancer. It's over there, right? Once you see the cancer, you detect them. Cancer is here, the tumor is here, and then shine the near IR onto it. They heat it up. Heat it to 60 degrees. This is like almost like 60 degrees. All the tumor, of course, burn out. The tumor, and then my students were really brutal. They're overkill, right? Burn a hole, the tumor is gone, and then after a couple of weeks, the new mice survive without the tumor. And with that, we can do the photo. Of course, like the components, electrical component, magnetic component, the same way. We can put a magnetic sensitive nanoparticle, inject the mice, and then put them into a coil and open the closed circuitry will generate the magnetic field, and the magnetic field will heat up the tumor cells, burn them out. Okay. All right. The reason is that my student, now Professor Ningxia University, he did this very ambitious, put all kind of platform together, diagnosis and heating and photodynamic therapy, all put there, and then also we can do the hydrogel. It's the same principle for the tumor and for the wound healing. Professor Chen also write a beautiful review article. If anybody have a chance to see it, it's a natural hydrogel material, and they use the other like couple as the anti-tumor agent for the detection and the chemotherapy, photodynamic therapy. All right. And then the same thing, that's a long article by my student, Xie Wensheng, now is a professor at the Beijing Institute of Chemical Technology. It's also talk about couple. But finally, just do a summary. Use green solar and photo energy may reduce the carbon emission, of course, that's link. Okay, solar distillation for fresh water has been quite successful in our lab, and then we try to scale them up. The photo-driven soft flow bath, that's fun stuff based on the witchmers. And the last is photothermal and photodynamic material for tumor therapy. All right, I have to thank National Science Foundation and Chinese Ministry of Science and Technology and many funding agencies. That's our group. Most work done by my students and my collaborators. And hopefully everybody have a chance to visit the Tsinghua, enjoy science, happy life. And then our new campus building is almost done. Okay. Hopefully next time you can visit our new campus building. Thank you very much.